Hi, everybody. Welcome to this week's class on present value. So hopefully you've seen present value before and in your Principles of Finance class. I think we're going to take it to a little bit of a deeper level in this class. So here's the contents for this slide deck. We're going to cover the basics of discounting cash flows, moving stuff backwards and forward in time, and the intuition there. And then we'll talk about shortcuts. So these are things like annuities, perpetuities. We'll define them. We'll talk about why we like them so much, why we'll use them basically in every class until the final exam. We'll use some of these shortcuts. We use these a lot in corporate finance. We'll talk about why we use them. Importantly, these shortcuts can also be moved backwards and forward in time. Just like you can move one cash flow 10 periods into the future, say, you can also move an entire stream of cash flows 10 periods into the future. Okay, and we're going to do that a lot in corporate finance, so we'll talk about that. And then at the very end, we'll talk about setting up present value calculations in Excel. So Excel's a computer. It can calculate things a lot faster than we can. So we like to have Excel do the work for us. And I'll show you kind of a parsimonious way to set up present value calculations in Excel and teach you a few tricks along the way that should be helpful in your careers. Okay, so discounting cash flows. Within this section, we've got these three things to talk about. We want to talk about the ingredients. What are the core pieces of the present value formula? We want to get at the intuition of them. So we don't want to just spit out a formula and just refer you to a formula and say, use the formula, plug it in. We want to try to get at the economics underneath the formula. In particular, we want to get at the intuition behind the time value of money and our discount rate. Right? The discount rate is a pretty subtle concept that we'll talk about a lot in this semester. It's so subtle that it's got like a million different names. You see them here. Sometimes R is called the discount rate. Sometimes it's called the hurdle rate, the expected return, required return, opportunity cost of capital. These are all synonyms for the discount rate. So it's such a subtle concept that we want to get at the intuition a little bit more deeply. And then we'll talk about additivity. So if you can calculate a present value for one cash flow, you can do it for 10 cash flows and add it up. And that's obviously going to be very important for us. Okay, so this is the beginning of corporate finance. You may feel a little bit like this.
I'll never understand the workings of high finance.
The goal for this class is to get you to feel a little bit more like this.
I just love looking through the business section. My name's on every page. McDuck assets top 200 bajillion. Delightful. McDuck stock reaches all-time high. Wonderful.
Okay, so how do we move from SpongeBob to Scrooge McDuck, right? The path is through this one very simple formula. The present value formula, you've seen it before. The present value of a cash flow is equal to C divided by 1 plus R to the T. What are the ingredients here? Well, C is some cash flow that you're going to get in the future, right? We're expecting to get C at time T. Okay, so right there, that's two ingredients. You've got C and T. Okay, R is the tricky ingredient here. This is the discount rate. We said it's got lots of different names: hurdle rate, required return, opportunity cost of capital. Okay, this is what we expect to earn on an investment with similar risk. Okay, so again, it's pretty subtle. We'll talk about that a lot this class, and that's why it's got so many different names. But the idea here is that there's a cost to waiting over time. There's a time value of money here. You need to be compensated for that cost, and R is picking that up. Okay, you put these three ingredients together, you calculate the present value. The present value allows us to compare this cash flow to the cash that's in your pocket. Right? You've got some money in your wallet right now at this instant. You want to compare that to some future kind of nebulous cash flow. And the present value is what lets us do this. So we have one formula to value everything, right? One ring to rule them all, one formula to value everything that we do in finance. So we've met this guy before. We've met Elon Musk. He's got these interesting companies, SpaceX. He launches stuff into space and makes money there. Okay, you can use the NPV formula to value SpaceX and his projects. The Boring Company, he calls it, with these flamethrowers and things. Okay, so you can put those cash flows into the formula and value the company. Likewise, let's say you're a manager at the Gap and you're thinking about working with Kanye West to get his Yeezy clothes into your store, right? Okay, so clothing's not going to be quite as risky as shooting stuff into space, but the project is still going to be dependent upon the creative output of an artist, right? It's still going to be kind of a hard thing to get a hold of, but in principle, if you use the formula correctly, you can value that deal for the Gap. If you're a manager at the Gap, you can value that deal with working with Kanye. Okay, or you can think about the more mundane. So obviously, Elon Musk and Kanye, those are on one end of a spectrum, very exciting deals. On the other hand, you've got Dunder Mifflin. It's a fictional paper company. They chose a paper company because it's just so boring. You can't think of anything more boring than paper. But you can compare. Kind of the magic of it is you can compare the Yeezy clothing line to Dunder Mifflin using this formula. Right, that's what's amazing about it. Or you can think about insurance. Okay, so down here we've got Ned Ryerson from Groundhog's Day, insurance salesman. Insurance is very different from everything else here. With insurance, you hope that you never get a return on that investment, right? You hope that when you buy home insurance, that your house never burns down, right? That's the hope. You're hoping that you're just putting money into it and you never get anything out. Okay, so insurance is a very different set of investments than companies, yet you can still, in principle, use the present value formula to value that. Okay. And then finally, we've got government debt. So this is a U.S. Bond that was issued a long time ago. Government debt's pretty safe, about the safest thing you can think of. You can use the present value formula to calculate the value of that debt as well. Okay, so one formula to govern a wide range of projects, put them all on an apples-to-apples basis, compare government debt to a paper company, to insurance, to the Gap's deal, to SpaceX, right? Put them all on an equal footing and compare them to each other. So now that we've talked about the promise behind the present value formula, I want to talk about the intuition. Why does it work? Okay. So first we'll talk about the intuition on the math side. And the math is pretty straightforward. All we're doing is moving stuff backward and forward in time. Namely, if you want to move things backward in time, toward the present, you divide by 1 plus r. If you want to move things one period toward the present, you divide by 1 plus r once. If you want to move things 10 periods closer to the present, you want to move things 10 periods into the past, then you divide by 1 plus r 10 times, right? Similarly, if you want to move things into the future, instead of dividing, you just multiply by 1 plus r. If you want to move things 30 years into the future, you multiply by 1 plus r 30 times, okay, where r would be your annual rate. Okay, so that's all that's going on with the math, is just this mechanical thing, moving cash flows backwards and forwards, dividing or multiplying. Now, the economics is more interesting, right? The math intuition is pretty straightforward. The economics is a little bit more subtle. To know how much you're discounting these cash flows, you have to hone in on the parameters, right? You have to hone in on R and T. Now, T is pretty simple. T is just the number of periods that you're moving things through time. R is more subtle, so I want to talk about the economic intuition behind R next. So R is capturing what's called the time value of money. And we all kind of understand the basics of this. You would rather have money in your pocket now than money in 10 years, right? If you'd rather have $1 in your pocket now than a promised dollar in 10 years from now. We all kind of get that intuitively, but it's worth breaking that down. Why exactly would you rather have money in your pocket now instead of money paid to you in 10 years? Okay. The thought experiment is this. That dollar that you're going to get in 10 years, you could compare that to having the dollar in your pocket now, but just keeping it in your pocket for 10 years, right? That would be analogous. Instead of getting the dollar in 10 years, you have it now, but you're just forced to keep it in your pocket for 10 years. Okay? That's obviously not as good as if you have the dollar in your pocket now and you can do stuff with the dollar, right? You could take that dollar and buy lunch or pay rent or invest, put it in the bank and earn a return, right? So keeping it in your pocket is one option, but you've got these other options, and those other options are valuable. So If you're forced to keep it in your pocket, then that's expensive. You're giving up these other options. Okay, so that's what we mean by an opportunity cost of money. You want to be able to do things with your money. You don't want to have to be forced to keep it in your pocket. If the cash flow doesn't arrive until the future, that's as if you're being forced to keep the money in your pocket today, and that's expensive. The second component for the time value of money is that the money in your pocket today is safe, whereas future cash flow is not. Okay, there's always some risk with a future payment. Even if the US government is promising to give you $1 in 10 years, you're never quite sure how much that's going to be worth, right? There's inflation and there's other things involved that can make that $1 in 10 years worth less to you than the $1 in your pocket, right? So there's always risk, and that risk obviously varies depending on the cash flow. So if Elon Musk, if we go back to this kind of board of possibilities here, if Elon Musk is promising you $1 in 10 years, that has a very different risk profile than if the US government is promising you $1 in 10 years. Okay, so that's part of the time value of money. That future cash flow gets discounted more if it's riskier in the future. Okay, so these are the two components of the time value of money. These are kind of the fundamental things that drive the formula, why it works economically, why those future cash flows are worth less to you today than the cash in your pocket. A higher R indicates a higher cost of 1 and 2 together. That's what drives R. Next, I want to talk about the size of the discount. We want to quantify that somehow. We've talked about the abstract reasons for the discount. We want to try to quantify it. So to think of an analog, when I go to the grocery store, I shouldn't do this, but I do. I go to the bakery, and usually the bakery has like a clearance shelf. It's got all the baked goods that have a best by date of like tomorrow or today. Right? These are things that they have to sell. They can't sell them in the next couple days, so they put them on clearance. They put them at a huge discount to try to get them off the shelves and then at least get some money off of them. Now, what determines the size of that discount? Well, maybe if the brownies expire today, they're sold at 20 cents on the dollar of what they would ordinarily be. If the brownies expire in 2 days, maybe it's 80 cents on the dollar, something like that, right? So there's some factors that determine how much you're discounting those baked goods. The same thing is happening with cash flows. We have factors that determine the size of cash flow discount. We talked about the discount rate here and T. We're going to put those together to see the size of the discount. We can do that with something called the discount factor. So the discount factor is equal to the present value of $1 in the future. Okay, so this is like 80 cents on the dollar for those baked goods. A discount factor of 0.8 would be that dollar is only worth 80 cents, right? It's the same idea. You're valuing something at 80% of what it would ordinarily be worth. Okay, the present value of $1 is maybe 80 cents if it's at a certain point in the future. Okay, so that's the discount factor here. It's the present value of $1 at time t with a discount rate of R. Sometimes you'll see the present value formula, which we all know and love, you'll see that rewritten in terms of the discount factor. Because if the discount factor is the present value of $1, then you can just multiply the discount factor by C, and you're recreating the present value formula. Okay, so it's not a new formula. I'm not inundating you with formulas here. It's the same formula, but the discount factor is sometimes a useful way to represent how much you're discounting the brownies. How much are you discounting those future cash flows? To give you a visceral sense of that, I just plot the discount factor here. I plot the discount factor for different discount rates. 2% would be the dash, or the dotted line is 2%, the dashed line is 5%, the solid line would be a discount rate of 10%, and I plot it as a function of the number of periods in the future. Okay, so let's start with the easy case. Let's start at time 0. How much do you discount a cash flow at time 0? At time 0, the money's in your pocket, right? So you don't discount it at all. So what's the present value of $1 in your pocket? Well, the present value is $1, right? It doesn't depend on what your discount rate is. It's in your pocket already. It doesn't matter what your discount rate is. It's in your pocket. So you're not discounting this at all. Here, the brownies are at full price. if you go to, say, the solid line of 10%, now you start to see some real action pretty quickly. All right, so this is maybe a dairy product that has a short shelf life. If it expires in 2 days, you're going to discount that a lot, right? If it expires in 1 day, then you're going to just give it out for free or something because no one wants to drink a gallon of milk, in a day, right? So these are things that just deteriorate over time very rapidly if you have a high discount rate. For example, if you have a cash flow that's 10 periods out and the risk of that cash flow is 10%, then that cash flow is only worth about 40 cents. Instead of getting $1 in your pocket today, if you are forced to get that 10 periods out, it's only worth 40 cents to you. Now, things improve a little bit if your discount rate is smaller. So maybe baked goods don't deteriorate as bad as milk. So maybe that's the dotted 2% line. 10 periods out with a discount rate of 2%, you're getting a discount. You're looking at a discount factor of about 80-some%. Right? So the price of those cash flows is about 80% of what they would be if they were in your pocket already. Okay, so this is just to give you a sense of how the discount factor is working and how it varies dramatically by the discount rate, right? A high discount rate makes a huge impact in a relatively short period of time. Okay, so enough with the abstractions. I want to talk about some examples now, make sure that we can use the present value formula to solve finance questions. I want to start with a relatively simple example, but I want to work in a few different ways to show you what the present value formula is capable of. So in this example, you're going to buy a computer. The list price is $12.95. However, the store doesn't require you to make the payment today. Rather, the store is going to give you credit so that you don't have to pay for 2 years. You're given a discount rate of 8%. So this is kind of a bit fanciful in today's world, but suppose you can earn 8% on your money in the next 2 years. How much money should you set aside today in order to make the payment in 2 years? Okay, so I'm going to work through this problem. Like always, I'm going to dock the slides on the right, and then I'll have the work on the left here. The first step to any present value calculation is to make sure you know the cash flows. In this example, there's only one cash flow. You bought the computer for $12.95, but you don't have to pay until time 2. Okay, so you can walk out of Best Buy right now without paying anything, right? Time 1, in 1 year from now, you don't owe anything to Best Buy. It's only at time 2 that you owe them $12.95. Okay, that's what the store credit means. So how much is that worth to you today, right? It's pretty far out there, so it's not worth $12.95 to you today. Let's work through the present value formula to see how much the computer costs to you today with a discount rate of 8%. Okay, so once we have the cash flows down, the second step is to make sure we know the formula. So we're going to use the present value formula. Pretty straightforward. So we've got the first 2 steps for any problem. Make sure you know the cash flows. Make sure you know what formula you should be using. Next, we want to make sure we put the right values into the formula. So in this problem, you just have one cash flow. So that C is $12.95. And the problem gives you a discount rate of 8%. And you know that the cash flow is occurring at time 2. So that's all of our parameters. So we have all the ingredients we need to calculate the present value of that computer. Present value is equal to $12.95 divided by 1.08 squared. Okay, and so you plug that into your calculator and you'll get $110.25, or $1,110.25. Okay, so this is the true cost to you. You only need $1,100 in your bank account today in order to make the payment to Best Buy at time 2. Okay. So let's check that, right? I'm kind of claiming that this is the cost to you, but let's check. If you have this amount of money today, will you have enough at time 2 to pay $12.95? Okay. Remember that the present value formula is the same thing as the future value formula. It's just a kind of rewritten thing. So if we have the present value here, we better make sure that this 11.10.25 is going to turn into $12.95 in 2 years. Okay, so let's check our work. We know that the future value of a cash flow is equal to the present value times 1 plus r raised to the t. In this case, we calculated the present value to be $1,110. We have the discount rate of 8%, and that's 2 years out. So if you put this into your calculator, you should get exactly $12.95. Right? So this is verifying if I have $1,100 now, and I can earn 8% like the problem says, then I should have enough to pay Best Buy at time 2. Okay. So okay, that's a pretty simple present value formula. Hopefully we're all comfortable with that. Let's add a little bit of nuance to it. We want to recognize that cash flows are additive. You may have multiple cash flows, and the present value formula is just additive. So if you have 2 cash flows, you just calculate the present value of each of those 2 cash flows separately, and then you add them up, right? So more generally, if we have a whole stream of cash flows on the right, cash flow 0, cash flow 1, 2, to t, to infinity, whatever, you can get the present value of all of that whole stream of cash flows by calculating the present value of each individual cash flow. So the present value of cash flow at time 0 is just the cash flow. Present value of the cash flow at time 1, you're discounting that once, right? The present value of a cash flow at time t, you're discounting that t times. You get the present value of all these individual cash flows, and then you just add them up. That gives you the present value of the entire stream of cash flows. Okay, so that's kind of the next thing we want to do with the present value formula is recognize that it's additive, and that's going to give us a lot more power, obviously. Note too that the discount rate can depend on the timing of the cash flows. So I put a little subscript here for R1. That indicates that the discount rate at time 1 corresponds to this cash flow. It may be different than the discount rate at time 2. This is R2. That may be different than R1, depending on what's going on with the cash flow at time 2. Right? Maybe the cash flow at time 2 is riskier than the cash flow at time 1, in which case you would need a higher discount rate. Okay. Or alternatively, if we think about the reasons why your discount rate varies, it could be the risk of the cash flows, or it could be what your other options are. And it could be that over a 2-year horizon, you've got different options than over a 1-year horizon, in which case your discount rate may be different over a 2-year horizon than a 1-year horizon, right? So it's a very general formula. We're going to do an example where we get into that, but I want to highlight it here that this is very general, right? We can have arbitrary cash flows, arbitrary discount rates. We're just going to add them all up to get the present value of the whole thing. Okay. Foreshadowing what we're going to do at the end of this lecture, a little bit of Excel can go a long way, right? If you've got a ton of cash flows here, you don't want to be doing this one by one. You don't want to be calculating each of these on your calculator. You're going to burn it out by the end of the semester. So a little bit of Excel can go a long way. So that's what we're gearing toward. And here's also a note about the discount rate depending on the timing of the cash flows. You may have different discount rates depending on the timing of the cash flows. Okay, so let's put this additivity to work in our simple example, right? This was a very simple example. We're going to just add one little twist to deal with the additivity. So same setup. You bought this computer for $12.95. The store is going to give you credit just like before, and you can make installment payments on it. Okay. Now, it's a little bit different than the first example. The first example, you just made one payment of $12.95 at time 2. In this little twist on the example, we're going to have to make 2 payments. Okay. In particular, you have to pay $600 in 1 year and then $695 at time 2. Okay, so it's still no payments due today. Okay, so if we go back to our original table, we can revise it. At time 0, still you don't have to make any payment today. But at time 1, now you do. Best Buy is being a little bit more strict in their payment. So you have to pay $600 at time 1, and then $6.95 at time 2. So Best Buy is being a little bit less generous. You can't put everything off to time 2. You have to make a little bit of a payment at time 1. Okay. Everything else is the same, though. The discount rate's still going to be 8%. Question is the same. How much money do I need to set aside today in order to make sure I can pay $600 at time 1 and $695 at time 2? Okay. So how are we going to solve this? Well, the setup's going to be similar to before. Let me clear some of this out. Okay. But instead of having just one cash flow at time 1, now we have 2 cash flows. Okay. So we're going to write the more general present value formula. We need a cash flow at time 1. We're going to replace the T subscript with a 1. And then we have a separate cash flow at time 2. We're going to add up the present value of each of those individual ones to get the total. All right, so what's our what's our cash flow at time 1? We have 600. Our discount rate's 8%. We add that to the 695 that we're getting at time 2. Okay, and that's it. We're going to have to plug those 2 things into our calculator. We'll get first payment, the present value of that $600 is about $555. The present value of the second payment, the $695, the present value of that is about $596. So in total, how much does a computer cost us today? It's going to cost us $11.51. That's how much we need to have today in our bank in order to make sure that we can make these payments to Best Buy in the future. Okay. And again, you can check it with future values. Right? If you have $555 today, you grow that one period at 8%, and you're going to get $600. Okay. If you start with $596 today, you grow that 2 periods, you're going to get $695. Okay, so you can always check your present value calculations by doing the future value with your answer. Okay. Notice here that the time value of money is kicking in. Because Best Buy was a little bit more stringent in their payments, the cost of the computer went up to us. Right? The cost of the computer is $11.51 now. It used to be $11.10. But the cost went up to $11.51. Why is that? Well, because we can't delay the payments. Best Buy is getting the money sooner. That means we have to part with the money sooner. And so that's costly to us. The exact cost is, $41. It's the difference between this $11.10 that we calculated earlier and the $11.51. That's the time value of money kicking in. Okay, so that's the second twist. That's the first twist, on the computer example. I want to do one more twist to make use of the present value formula. Okay. The second twist deals with the discount rates. We said that the discount rates don't have to be the same for each cash flow because you may have different options depending on the horizon, for example, or on the risk of the cash flows. Your discount rates may vary. So let's see how that would affect this example. Same exact problem. The computer still costs $12.95. Okay, the store is still going to give you credit. Okay. And in fact, the cash flows are going to be the same as before. Best Buy requires you to pay $600 at time 1, and they require you to pay $695 at time 2, $600 at time 1. Okay, so that's all the same. Okay. Here's the wrinkle. You can earn 8% per year if you invest in a 2-year CD. Okay, so with a certificate of deposit, you put your money at the bank, you earn a return. The catch, however, is that you can't touch the money for 2 years. Okay, so it's a 2-year CD, you can earn 8%, but you have to leave the money there for 2 years. If you take it out before, you have to pay a big penalty. Okay. You also have the option to put the money in your checking account, which is only going to earn 2% per year. Okay. The question now becomes, how much does this computer cost you if these are your options? The setup is going to be the same. We need to calculate the present value of these payments. We've got a cash flow at time 1. Now we have a special discount rate at time 1, which may not be the same as the discount rate at time 2. So to indicate that, I put subscripts on the discount rates. Okay, before I just had one discount rate. I had 8%, but now R could vary. Okay. Economically, how much can we earn in 1 year? What's our cost of capital over a 1-year horizon so that we make this first $600 payment? In short, what is R1? Well, we can't earn 8%. That's impossible over a 1-year horizon. In order to earn 8%, we need to keep it in the CD for 2 years. So we can't earn 8%. The only option we have over a 1-year horizon is 2%. You have to put the money in your checking account, earn a little bit of money, and then use that to pay Best Buy at time 1. Now, over a 2-year horizon, we've got more options. Right? Over a 2-year horizon, you could put the money in your checking account and earn 2% over those 2 years, but that wouldn't be very smart, right? You can do better by putting money in your CD. If you put the money in the CD, you'll earn 8% per year for 2 years. Okay, so that's your true economic cost. So you want to reflect that in your present value calculations. You could earn 8% over a 2-year horizon. So now that we've pinned down the cash flows and we pinned down the discount rates that correspond to those cash flows, we just plug them into our formula and calculate the present value of each cash flow and sum them up. Okay, so the present value of this first $600, that's $588. The present value of the second period, $695 cash flow, that's $596. You put them together and you get $1184. So this is the true cost to us of the computer. It's not the $12.95 that is the list price. The true cost to us is $1184. Again, you can check this. Put that $588 in your checking account. It's going to grow to $600 in a year. Put that $596 in your CD. It's going to grow to $695 at time 2. So these two things show that you can hit these 2 payments. Okay? And therefore, the true cost, what you need today, is $1184. I want to pivot next to future values. Okay? So as I was showing you, when we check our work, any present value formula we do, you can check it by looking at the future values. This is just a reminder that it's not some new formula. You don't have a bunch of formulas to keep track of. It's the same formula. Right? The present value formula here can just be rewritten to calculate the future value, just one step of algebra. Intuitively, the future value is picking up something different than the present value. Right? The present value is recognizing that we discount things that happen in the future. We don't value them the same today. We have this discount factor, right? We mark them off. The future value is answering how much money will your present dollar grow to at time t if you have a growth rate of R. Okay, so for example, if you start with $500 and you can earn 5% on that over a 3-year horizon, then by time 3, your money should grow to $578, for example. Okay, so we can do a few different examples just to make sure that we're comfortable with the calculation here. So what's the value of $300 at 8% for a year? Well, you just multiply the $300 at 8%. That gives you $324. Okay. How about the value of $300 at 8% over 8 years? Well, same thing, just plug it into your present value formula, manipulate it to find the future value, and you get $555. That initial investment grows to $555. Okay. I want to note here something that's very important. There's not just one future value. Okay. The future value depends on what time you're sitting at. Okay. Notice that you started with the same $300 in both of these 2 examples. $300 today, earning 8%. $300 today, earning 8%. That's the same. The difference is what year are you sitting in the future? So this would be future value 1. This would be future value 8. Right? There's infinite potential future values that you could find. You could find the future value of that money at time 3 or time 100, time 86, whatever. You can find a million different future values. So when we talk about a future value, you need to specify what time we're talking about. Okay, so here we're talking about future value in 1 year, here it's 8 years, but the future value is kind of not specific enough, right? You have to really pin down what point in the future you're referring to. This is different than present value, right? With a present value, there's just one present. There's only one times 0. We know what that is. Future value isn't as precise. Here's a picture of different future values. So this is very similar to what I drew with discount factors. I use the same rates here. Here's a discount rate of 2%, discount rate of 5%, and a discount rate of 10%. And instead of drawing how the discount factor changes over time, I'm showing what the future value is over time. Okay, so this is basically the flipped picture of the discount factor. If you're investing at 10% over 10 years, then $1 today is going to grow to about $3 at time 10. Okay, that should sound about right, because if you remember the discount factor figure, we saw that $1 at time 10 with a 10% discount rate, we're only valuing that at like 30%. Okay, so the fact that that dollar grows to $3 in the future, that's the same, right? You multiply it by 3, or you divide it by you multiply it by a third to get the discount factor, right? That lines up. It's basically the same calculation here, but it's just showing you the other side of it, how things kick up exponentially. Okay. Just like present value is additive, so is future value. You just move every single cash flow you have to time t. Okay, and so here it's important that you specify what time you're moving everything to. So if you have a cash flow at time 0 and you want to move it to time capital T, you have to move it t times into the future. If you've got a cash flow at time 1 and you want to move it to time t, you don't move it t times anymore. You move it t minus 1. Okay, and likewise, if you've got some cash flow at little t, how many times do you move that to get it to cap t? You move it big T minus little t, right? So you got to move all the cash flows to the same time period. Okay, and here's a note that I said before. There's an infinite number of times that you could move cash flows to, so you have to specify which future period are you talking about. Okay. So let's do some examples with future value. Make sure that we're comfortable with those mechanics. In this case, you're saving to buy a house. You're going to save $10,000 per year starting in 1 year. Okay. So time 1, you're going to save $10,000. And you're going to do that for 3 years. You want to know at the end of 3 years of doing this, how much money are you going to have so that you can make a down payment on a house? So I'm going to add a column to the right here. Now we're not interested in the present value anymore. We want to know the future value at time 3. This $10,000 that we save at time 1, that's going to grow to time 3. This $10,000 that we save at time 2, that's going to grow to time 3, et cetera. We want to know in sum how much we're going to have at time 3 if our discount rate is 5%. Okay. So first step for any problem, draw out the cash flows. Here we go, nothing at time 0, 10,000 at time 1, 2, and 3. Second step, know what formula we're using. So here we want to calculate the future value of all these cash flows at time 3. If we have a cash flow at time 0, how many times do we move that to get to time 3? Well, we multiply it by 1 plus r 3 times. Okay. If the cash flow is sitting at time 0, you multiply it by 1 plus r once to get it to time 1, twice to get it to time 2, 3 times to get it to time 3. So you multiply by 1 plus r 3 times to get to time 3. If we have a cash flow that's sitting in time 1, now we only have to move it twice. Right? We move it once to get to time 2, we move it one more time to get to time 3. That means we multiply by 1 plus r twice. The cash flow at time 2 we only need to move it one time. And then how many times do we have to move the cash flow times 3 to get it to time 3? Well, we don't have to multiply that at all, right? It's sitting in time 3 already, so we don't have to calculate any kind of future value. It's sitting where we want it. Okay, so that's the second part of any problem. Make sure you know what you need to do to each cash flow to get the answer. And then the last part is plug in the right numbers. Okay. So the future value at time 3, how much cash do we have at time 0? Well, we have $0 at time 0, so cash flow at time 0 is just 0. You can ignore the rest. Then we get $10,000 at time 1. We multiply that by 1.05 raised to the 2. Right? We have to bring that first cash flow 2 periods to get to time 3. We have to bring the second cash flow 1 period to bring it from time 2 to time 3. And then that last cash flow, we don't have to touch at all. It's sitting exactly where we want it to. So we put all of that into our formula. And that gives us 31,525. If you want to go into more details, how much does that first cash flow grow to time 3? That'll grow to 11,025. Plug that into your calculator. The second cash flow is only going to grow once at 5%, so it's only going to grow to 10,500 by time 3. And obviously, the last cash flow is sitting where we want it, so we don't move that at all. Okay, so you see that's how we can do future value and make it additive. We just move every single individual cash flow to the same time period. Another way to do this, you should be able to check, is to calculate the present value of all of these cash flows. Okay, so instead of moving them all to time 3, what you could do is you could move all of those cash flows to time 0. Okay, so let me show you what you would get there. If you get the present value of all those cash flows, I don't have that offhand, but you can calculate the present value of 10,000 divided by 1.05 plus 10,000 divided by 1.05 squared plus 10,000 divided by 1.05 cubed. Right? You calculate this thing, and then you can bring that whole thing to the future 3 times. Okay, so that may be a little bit easier, maybe a little bit cleaner to think about, to calculate the present value of everything and then move that whole sum forward 3 times, and you should be able to replicate this 31,525. Okay, so again, you can always check your work by doing the opposite of what you did, right? If you calculate present values, you can calculate future values to check your work, and vice versa. Okay, that brings us to net present value. Now, net present value isn't anything new, right? The formula is going to be the same, right? This is the same formula we had before when we had additive present values. Just take the present value of every single cash flow and add them up. Now, net just indicates that some cash flows are going to be positive and some are going to be negative. Okay, so on net, do the positives outweigh the negatives? That's all that we mean when we say net present value. Calculate the present value of all the positives, you subtract out, you net out the present value of all the negative cash flows, and then what's left determines whether the good outweighs the bad. Okay. So for example, suppose you have a $500 payout in 3 years, you have a 5% discount rate, and you have a $400 investment that's required today. So you have to put $400 in. That's a negative cash flow that occurs today. And in exchange, you get $500 in 3 years with a discount rate of 5%. What would be the net present value? Well, the present value of the negative cash flows is minus 400, obviously. That happens today. You lose $400. The present value of the positive cash flow is 431. It doesn't occur until the future, so you have to discount it. It's worth 431 to you today in present value terms. So on net, what's happening, you put all of it together, the net present value is about $32. Okay, so nothing new again. The problem sometimes students have in principles is it looks like you have a whole bunch of formulas. We're just doing one formula just over and over again, but sometimes we call it different things. Okay, that leads us to the NPV rule. We said that the net present value is calculating the value of the positive cash flows less the value of the negative cash flows. We said way back in the beginning here that the present value calculation is putting all the cash flows on an apples to apples basis. So you can compare the positives to the negatives. And if the positives are worth more than the negatives, if your net present value is greater than 0, then that means it's a good deal. That means that the good cash flows outweigh the bad, and so you should take that project. Okay? Now, so that gives us something called the NPV rule. You should take projects where the NPV is positive. If the NPV is negative, you should not take it. These are going to be the steps we'll follow for NPV analysis throughout the entire semester. The steps are going to be basically the same. Obviously, the level of complexity that we add to it will change, but these basic steps will be there. The first part of any NPV analysis is to project the cash flows. Today, I've just been giving you the cash flows, right away, but later on, I'll give you, say, accounting information, and then you'll have to figure out the cash flows. The second part is to make sure you know the discount rate. Again, today, I'm just giving you the discount rate. But later on, after the first midterm or so, I'll have you estimate that. Once you have these things, so once you have the cash flows and the discount rate, then we're in class 1 of this semester. You just discount those cash flows, and then you're going to apply the NPV rule. Okay. So we'll do one more example with NPV. Suppose you want to value a construction building. You want to build an office building and then sell it later on. Okay. At time 0, you have to put in a lot of money to build this building. And likewise, at time 1, it takes a long time to build this building, so you have to spend $150,000 at time 0 and $100,000 at time 1. And then finally, if things work out at time 2, you're able to sell the building for $300,000. Okay, so the question is this a good deal or not? Should you undergo this construction project if you're, if you're a home builder, if you're a apartment builder? We're given a discount rate of 7%, so we have everything we need. We have the cash flows, we have the discount rates. We just plug it into our present value formula and see whether the good cash flow here, the time 2 cash flow, is that better or worse than these negative cash flows, these negative $150,000 and $100,000 at time 0 and 1. Okay. So you've already got the cash flows. I'm not going to fill out this table. We already know the cash flows. We know what the discount rate is. So we can just work through the equation. We know that the NPV is going to be that negative $150,000 at time 0 plus a negative $100,000 at time 1, discounted at 7%. And then finally, we have the good cash flow, $300,000 at time 2. Again, discounted at 7%. Okay, so you put all this into your calculator and you get a positive NPV. So you have minus 150,000, you have minus 93,500, and then finally you get the payoff of about $262,000 at time 2. You can see that the $262,000 is bigger than the sum of the 150 and 93.5. So this is a positive NPV project. You should take it. These shortcuts are things that we're going to see from now until the final exam. So putting in the effort now, putting in the investment now, I think is going to pay big dividends going forward. The idea here is that sometimes we'll get special streams of cash flows. Think of an annuity or a perpetuity. These are very kind of particular streams of cash flows. And rather than calculate the present value of each individual cash flow and then sum them up, which is a little bit tedious, and especially if you're on an exam and crunched for time, say, or especially if you've got an infinite stream of cash flows, right? If you got a perpetuity, you have an infinite number of cash flows, you can be working on your calculator till kingdom come and you'll never get the present value. So we have some shortcuts that are going to help us value these very special particular streams of cash flows. Here are the 4 shortcuts that we're going to C, the perpetuity, the growing perpetuity, the annuity, and the growing annuity. I'm going to define them, and then we're going to talk about why they're important in corporate finance and how they're going to help us think about firm valuation. Okay. So the first is a perpetuity. Okay. As the name suggests, it's perpetual, right? It goes on forever. Cash flows forever. You get a constant cash flow C here. You're getting it at fixed intervals, so you get a payment C at time 1, you get one at time 2, time 3. These are evenly spaced out, okay? And they go on forever. Okay? So if we wanted to, we could value these just like we value every other cash flow, right? The present value is the present value of this first cash flow, C divided by 1 plus R, plus the present value of the second cash flow, C divided by 1 plus R squared, plus the value of this, right? On and on. But the problem is there's an infinite number of them, so you can't do that. Fortunately, we have a very nice shortcut. It's almost amazing how elegant it is, how well it works out. The present value of that infinite stream of cash flows is simply the payment, C, divided by your discount rate, R. Okay, so an infinite stream of cash flows, you just divide the size of each one of those cash flows, C, you divide that by the discount rate, and you're done. Okay. With all of these shortcuts, it's very important to keep in mind the timing of the first cash flow. Here, if you look at this diagram, nothing is going on at time 0. That's going to be true for all of our shortcut formulas. Nothing's going on here. This is something students are going to mess up. It's just undeniable. Someone's going to make this mistake. A lot of people are going to make this mistake on the timing. Nothing's going on at time 0. The first cash flow is arriving one period ahead of the present, right? Time 0 is the present. The first cash flow is one period ahead. When we use this shortcut formula, the first cash flow is one period ahead. That's why I put this subscript 1 here to reiterate that the present value is at time 0. The cash flow is arriving at time 1. Okay? So that's going to be important to keep track of the location of this value. But it's pretty amazing, really. I mean, present value of an infinite stream is just C divided by R. These do exist in the real world. So a little bit of history. The British government had a lot of debts from the Napoleonic Wars. They decided to consolidate all of these different types of debt into a perpetuity. They call these things consols. And to my knowledge, they're still trading. It's possible that you could, trade one. They're a bit esoteric, so I don't know anyone who owns these things. I don't own any of them, but in principle, you could. So why do we like perpetuities? They're obviously not a very important part of the financial markets per se. But if you think about it, what else lasts in perpetuity? What else goes on perpetually as a going concern? What has a no end date? What type of entity pays cash flows out as far as we can see? Well, firms do that, right? Equity does that. We think that these things are long-lived companies. They're going concerns, I say, in accounting, there's no end dates in sight. So one shorthand for valuing them is as a perpetuity. And so that's going to help us think a little bit about firm valuation by using such an elegant formula here. This is going to really help us hone in on some of the drivers of firm valuation. Okay. So we can do a quick example here. Suppose you have a console that's a perpetuity. It pays £5 per year, and the discount rate is 10%. What is the value of the console? Well, we'll go back over to our document over here, draw out this timeline, time 0, 1, 2, 3, skip a few, 99, skip a few more, forever and ever. We've got all these cash flows. When do the cash flows start for perpetuity? Well, they start at time 1. Okay, so at time 1, we're going to get £5. Time 2, we're going to get £5. 3 on and on. We're going to get £5 forever as far as you can see. So you look at those cash flows, you draw them out, and you realize this is a perpetuity. Get rid of that. Therefore, we know how to value it. Right? So the value of the perpetuity sitting at time 0 is C divided by R. We know that C is 5 pounds. Discount rate is given at 10%. So therefore, the value of this perpetuity must be 50 pounds. So that's how we would solve a run-of-the-mill perpetuity problem. The next special stream of cash flows is called a growing perpetuity. Now, it's like a perpetuity in that it goes forever. It's also like a perpetuity in that the cash payments are made at regular intervals, right? So you're getting a payment at time 1, getting a payment at time 2, getting a payment at time 3, right? Just like a perpetuity. What's different is that the cash flows are growing. So at time 1, you get C. At time 2, the payment grows by G%. It's growing at a rate of G. Likewise, at time 3, the cash flow has grown by G% again. So it started at C, it grew G%, so now at time 2, we're at C times 1 plus G. At time 3, we're at C times 1 plus G squared. It's grown by G% twice now. Okay, and this goes on indefinitely in perpetuity. If you want to value it just like any other stream of cash flows, you discount each individual cash flow here and add up all the results. Obviously, that's a pain to do when you have an infinite number. It's doubly a pain here because each cash flow is different. Right? With a perpetuity, the cash flows were the same, so that wasn't too bad. But here, each cash flow is different, and keeping track of the cash flow at each period is a bit of a mess. Fortunately, we have another shortcut formula for this. Again, it's kind of amazing how simple it is. The present value of that growing perpetuity is that first cash flow, C1, okay, divided by R minus G. So divided by the discount rate less the growth rate. Now C1, again, with all the shortcuts, I'm going to keep reiterating that for every shortcut we see. The first payment occurs at time 1. So if you look at this timeline, nothing's happening at time 0. Nothing's happening in the present. The first cash flow is happening at time 1. If you look at the formula, what's nice is you don't need to know any of the other cash flows. All you need to know is that first cash flow. You don't need to know the 10th cash flow after it's grown 9 times. You don't have to keep track of any of that. All you need to know is that first cash flow that occurs 1 year ahead of the present here. That's going to give us the present value is C1 divided by R minus G. Okay. The next shortcut is an annuity. Oh, and I should mention here, so there's no such thing as a growing perpetuity in the financial markets that I know of, right? You can't trade one of these. But this is going to be the go-to for firm valuation and for stock valuation. If you think about something that goes on forever but that's increasing at kind of a steady pace, that's a growing perpetuity, and then that is going to be a very helpful representation for firms and for equity. So we're going to see this a lot again. Till the very end of class, we're going to be working with growing perpetuities because they're such a nice shorthand. The next shortcut is the annuity. So hopefully we're familiar with annuities. They're a lot like a perpetuity in that you're getting a constant payment C. The payment is occurring at fixed intervals. That's time 1, time 2, time 3. You get that same payment C just like a perpetuity. The only difference here is that there's a fixed end date. So at time capital T here, the annuity is done. It's not going to pay any more after time T. So unlike the perpetuities, this is something that you could feasibly do on your calculator or on a computer. You just discount each individual cash flow, add them all up. There's a finite number of cash flows, so you could do this. It's not practical all the time, but you could do this. There's lots of these in the real world. So if you get a mortgage, your mortgage is going to be structured like an annuity. Car payments are going to be structured like an annuity. There's different ways to save for retirement. We'll see an example like that in just a moment that are structured like annuities as well. So these things do show up all over the place. If you want to value it, before I show you the formula looks kind of messy. So before I do that, I want to show you kind of the intuition here. An annuity is just the difference between two different perpetuities. If you have a perpetuity that starts at time time 1 and goes on forever, right? So it goes on to time t and goes on forever and ever and ever. Then you have a second perpetuity that starts paying right after time t. Okay, so you've got a perpetuity that starts paying right after time t, and then that goes on forever. If you want to recreate an annuity, all you need to do is subtract the second perpetuity that starts at t plus 1. You subtract all those cash flows from this first perpetuity up here that's going on forever. And if you do that, all you're left with are these first t cash flows. And so you can recreate an annuity as the difference of two perpetuities. The perpetuities have different starting dates, but they're just perpetuities. And we know that perpetuities are very easy to value. And so if you calculate the present value of these two perpetuities and take the difference, you're left with a annuity formula. Okay? And that's where this annuity formula is coming from. I work it out in the text that I posted on Teams, how you can derive this formula. Don't worry about the derivation. I'm just a little bit worried that this formula is a little bit ugly. But if you can see that it's just two perpetuities differenced out, then maybe that takes away some of the mystery and the intimidation of this this formula, right? C divided by R, that's a perpetuity. C divided by R here, that's another perpetuity. It's just this perpetuity sitting in time t. So it's a bit of an ugly formula, trying to demystify it a little bit. Okay. As promised, all these shortcut formulas have the payment starting in one period. Okay, just like all the other timelines, the annuity timeline is no different. Nothing's going on at time 0. The first cash flow is occurring at time 1. Okay, and so what shows up in the formula, it's just the cash flow that you're getting at time 1. Okay, you multiply this by this ugly bracketed term, 1 divided by R minus 1 over R times 1 plus R to the t. So let's do an example, make sure that we can work through this formula. We want to be very careful with the order of operations here. We've got brackets, we've got fractions. So I encourage you to work through as many examples as you can. Build the muscle memory so that when you're doing this on a test, you don't even have to think about the order of operations, right? You just know how to do it. And I'll show you my process in this example here. Okay, so dock the slides over here. Okay, so someone has a mortgage. Say it's got a 10% rate, and it's a 30-year mortgage with an annual payment of $6,000. So we'll just assume everything's annual. This 10% rate, that's an annual rate. Annual payment is $6,000. We want to calculate the value of the mortgage. How much does she owe on the house if you know this about her loan? Okay, so first thing, as always, we're gonna draw out the cash flows, or at least a subset of the cash flows. So we have time 1, time 2. We'll skip a few, and then we'll get to time 30, right? There's a 30-year mortgage, so we got to get to time 30. We'll go to 29, 30, 31, 32, into infinity. All right. We know the cash flows. The cash flows are given at $6,000. That's how much you're paying. So at time 1, right? So again, very important. Nothing's going on at time 0. With all of these shortcuts, the first cash flow is arriving 1 period out. Okay, so that first payment is at time 1, that's $6,000. It's a 30-year mortgage, so you're going to have to pay that $6,000 every period till time 30. And then after time 30, it's done, right? The annuities have a fixed end date. The date is 30 years out. So after that, nothing happens, 0, 0, 0. Okay, so those are the cash flows. We see that this lines up with this timeline here. Nothing going on at time 0, constant payment for a fixed end date. So you recognize, eureka, this is an annuity. Right? That means we can value it using the annuity formula. Okay. What is the value of an annuity? It's the cash flow divided by the discount rate. So I'm going to write the annuity formula a little bit different. I'm going to pull out the discount rate here. Sometimes you'll see it this way that's in the slide. Sometimes you'll see it the way that I write it up in the work. You know, they're equivalent. It's just whatever is easiest for you. Okay, so the value of an annuity is C divided by R multiplied by this big ugly bracketed term of 1 minus 1 divided 1 over 1 plus R raised to the T. Okay, so we have the formula. We know what it is. All we need to do is plug in the appropriate values into the formula. So we know what the cash flow is. We're getting $6,000 every period. Let's go back to this example. The discount rate is given at 10%. And we know how many periods there are. We know that there's 30 years on the mortgage. So there's 30 annual payments that we're making. So we have everything we need. We're going to put those values into the formula to get the value of the annuity at time 0. Right there, the present value of the annuity. I'm going to walk through how I would calculate this, you know, piece by piece to make sure that you get the order of operations right. Really, the best way to practice is to just do this over and over, so you don't have to think about it when you see it on an exam. So the first thing I would do is I would say, well, the $6,000 divided by 0.1, that's 60,000. Okay, so take care of that, and now I'm going to work on the inside brackets. I know I need to do the exponent first, right? The exponent comes before you do the division, so I'm going to keep the 1 minus 1 divided by. I'm going to calculate 1.1 to the 30th. That comes out to about 17.45. Okay. Next thing, I'm going to work inside this bracket. I have to do the division inside the bracket before I do the sum or the subtraction here. So we have 60,000 times 1 minus 1 divided by 17.45. That works out to about 0.057. Okay, so we're left with 60,000 times about 0.943. And that all works out to about 56,600 would be what your friend owes on the mortgage. That would be the value of the annuity. If you know calculator functions, if you're good with using calculator functions, feel free to do that for annuities. You know, I don't really know them. I just like to work it out and see each step myself. But if you're comfortable using things on your calculator, that's fine. On a test, as long as you tell me what you're doing, you have to tell me it's an annuity, and I use these values. I plug these values into the annuity formula. As long as you tell me that's fine. Whether you do it step by step like I do, or whether you use a calculator function, I don't care. Okay. This is an important point. One of the reasons why we like to use these shortcuts is because we can move them backwards and forward through time. So I can value a company as a growing perpetuity, say, that starts far off into the future. Maybe I forecast the cash flows for a company for 5 years. But then what happens after year 5? Well, I just kind of say it's probably going to be a growing perpetuity at some point into the future. So I have to be able to recognize that growing perpetuity starts, 5 years out or 10 years out. And then I have to bring that all the way back to the present. Okay, so my point is these shortcuts can be moved through time just like any other cash flow can be moved through time. Okay, so I want to work through an example to show you how to do that. We'll do it with a annuity here. Okay, and again, this is a very common thing for retirement. If you want to save for retirement, one way to do that is to buy an annuity. But the annuity doesn't necessarily start paying right away. Right? When we do these cash flows here, we're at time 0, and the first cash flow occurs at time 1. Okay, just one period out. But if you're saving for retirement, if you're, if I'm 30 years old, 33 years old, and I want to save for retirement, it doesn't do me any good to buy an annuity that starts paying off 1 year from now, right? I'm not going to retire at 34. You want to have an annuity that starts paying when you retire. Okay, so that's the spirit of this example. We're going to have an annuity that doesn't start paying until the future, but we want to know how much would it cost me now to set this up. Okay. So in this annuity, you want the annuity to pay you $30,000 per year for 20 years. So think you retired at 65. You want to have this payment of $30,000 until you hit 85. Right? That's one way to kind of cushion your retirement. But you're saving for retirement. You're not retired yet. You're saving for retirement. So you don't need the payments to start right away. You're going to have the payments start in year 16. Okay, you're still going to work for 15 years, and you want that first payment to occur in 16 years. Okay. We have an annual discount rate of 5%. How much is this annuity going to cost you today? Okay, so let's draw out the cash flows. Again, that's always the first part. We'll be able to see exactly what's going on once we draw out the cash flows. Okay, so we're at time 0. We want to know how much this annuity costs. How much is the annuity going to pay off in year 1? Well, 0, right? We don't want it to pay off until we retire. Likewise, at time 2, how much is the annuity going to pay us? 0, right? We don't need anything until we retire. When are we going to retire? We're going to retire in year 15. Okay. That's what the problem says. You're going to retire in 15 years, and then you actually don't want a payment in year 15. You want the payment to be made in year 16. So even at year 15, you're going to get 0 cash flow. The first payment occurs at time 16, and then you're going to get the first $30,000 payment. Okay. The annuity is going to go on for 20 years after that. So if you start at year 16, you want to get paid 20 times. So that takes us to year 36. And then after that, it's an annuity, so it has a fixed end date. So there's nothing after those 20 years. So year 37, you get nothing. We're back to 0. But for year 16, you get $30,000. For year 17, you get $30,000. And up till year 36, you're getting $30,000. Oh, actually, sorry, this is 35. If you're getting paid 20 times, it goes from 16 to 35. Sorry about that. That's you gotta keep track of when the starting point is. Okay, so 16 to 35, you're getting 20 payments of $30,000. So let's value this. How are we going to value it? The key here is we know there's an annuity somewhere. Right, the annuity starts in year 16. It starts paying in year 16, and it goes for 20 years. So that's an annuity. We know how to value that. The whole trick of this problem, though, is that the annuity valuation sits one period before the cash flows start. So the cash flows start in year 16. Where is the value of the annuity sitting? It's sitting in year 15. Okay, so let me write that out just to be clear. We know this is annuity. But where's the annuity sitting? It's sitting one period before the cash flows start. Cash flows start in 16, so the value has to be sitting in year 15. Okay. Once we recognize that, though, the rest is the same. We just have the same old annuity formula that we've just saw and we just worked with. So we've got some constant cash flow, we've got a discount rate, and we have the number of payments. We know that there's going to be 20 payments in this annuity. So that's the formula. We can plug in what we know, the parameters of the problem, $30,000 cash flow. We know that the discount rate is 5%. and we know that there's 20 payments. Okay, so again, how would I do this? If I were calculating things piece by piece on an exam, I'd first do this outside 30,000 divided by 5%. That gives us 600,000. And then I would work on this ugly bracketed term. First, I would calculate the denominator, 1.05 raised to the 20th. That works out to 2.68, or 2.65, sorry. Okay. Next, I would work inside this bracketed term. I'd calculate the fraction. So we've got 600,000 times 1 minus about 0.38. So that's equal to 600,000 times about 0.62, which gives us 373,000 roughly. Okay. So that's the value of the annuity sitting in year 15. Oops. Okay. It's the value of an annuity just from a straightforward annuity formula. The only subtlety is that we're sitting in year 15 because the cash flows start in year 16. Okay, so that's a stumbling block here. The question is asking, how much will the annuity cost you today? Right? You're not sitting in year 15. 15 is when you retire. You still got 15 years to work before you retire. So this whole valuation is sitting in year 15. How can we bring that to the present? We want to know the present value of the annuity, of this kind of special annuity. Well, the present value is going to be the value of the annuity that's sitting in year 15. And what do we have to do to that? Well, we have to just discount it back 15 times. Okay. So this is what I mean. Just like you can move any cash flow through time by dividing it or multiplying it, you can move these shortcuts through time the same exact way. So in this case, we want to move the annuity toward the present. We have to move it 15 times. So we already know the value of the annuity is about 373,000. We know the discount rate is 5%, and we know that we've got to move it 15 times to bring it to the present where we're sitting. Hence, we can calculate the total, the present value of this annuity that doesn't start for another 15 years. We can calculate the present value as about $180,000. Okay. So if you're hoping to retire in 15 years and you want to get these payments when you retire, you need to have $180,000 on hand in order to purchase that annuity. Okay. So if you're comfortable with this, then I think you're in very good shape. We're going to be seeing this type of logic over and over again, starting right before the first midterm, I think, is when we'll start to see this type of movement of shortcuts through time. Okay. The last shortcut to cover is called a growing annuity. So as you've probably put together by now, you put 2 and 2 together, this is like a growing perpetuity, but it has a fixed end date. It's an annuity that has an end date. So like a growing perpetuity, you're getting payments at fixed intervals, okay? And those payments are increasing period by period. So you start with some payment C, that increases by G% at time 2. You increase it further, G% to time 3. So now it's grown G% twice to get to time 3, etc. You grow it every period until time capital T. It's an annuity, so it has an end date. It ends at time capital T, and then nothing happens after that. Like any other stream of cash flows, you can just calculate the present value of each individual one, add them up. But we have a shortcut that avoids all that kind of calculator crunching. We have this growing annuity formula here that looks a lot like the annuity formula, except you've got R minus G instead of R, and then you've got this 1 plus G in the numerator here. So this is a particularly ugly formula. Where will we see this? So you don't see a growing annuity in the financial markets, just like you wouldn't see a a growing perpetuity, you can't trade it necessarily. But again, just like a growing perpetuity helps us think about firm valuation, so will a growing annuity. So in particular, this is a common way to think about startups, for example. If you think about a young company, it's just getting started, it's going to have a period of fast growth at the beginning. However, that fast growth is not sustainable. It's the brand new thing. It's got lots of room to expand and gain market share if it's just starting out. So it's going to grow fast to begin with, but at some point it's going to reach some steady state, right? At some point it's going to saturate the market. Walmart can only grow so much. It grows very fast when it's young, but at some point there's going to be a Walmart in every town, and then it can't grow too much. Or Starbucks, for example. All these companies have initial very fast growth, and then it stabilizes. So what would be a shorthand way to value a company like that? Well, you would have a two-stage growth model. You could have the first stage be a growing annuity, where you have a high growth rate. Then at some point, things are going to slow down, and then you can model the company as if it's a growing perpetuity. So it's some equilibrium state of a lower level of growth, and that lower level of growth just persists indefinitely. Okay. So one way to value the company is you value this growing annuity, and then you value this growing perpetuity, and then you add them up. Okay. Just like we move the annuity through time, one thing you would want to do with this company is to move this growing perpetuity back to time zero. Right? If I'm trying to figure out what's the present value of Starbucks sitting in the year 2005, I say, well, it's going to grow like this for 15 years. It's going to grow very fast for 15 years, and then it's going to grow kind of more slowly thereafter. What I would want to do is make sure that when I value the growing perpetuity formula is going to put the value of the growing perpetuity here. I would need to discount that all the way back to time zero, just like we moved the retirement annuity from time 15 to the present. So this is an example where you'd see a growing annuity in firm valuation. Next, I want to turn to Excel. Excel is going to be very helpful for us. It's going to be helpful in your job. It's used everywhere. I think it's kind of the language, these spreadsheets that the language companies use to kind of talk to themselves and talk to each other. And it's also going to help you check your work. So if you've got a lot of cash flows, you can have Excel calculate present values of a ton of cash flows very quickly, right? It's a computer. It can do these things without any problem. It's going to help you get comfortable with these formulas as well. If you're looking at the annuity formula, you don't trust it. I mean, that was my sense when I was first learning this. I don't know what's going on in this annuity formula. I don't have a sense for it. I don't feel it. I don't trust it. I want to verify. So you can do that in Excel. You can draw out each and every single cash flow pretty easily in Excel, and then check that it's giving you the same thing as what you did in the annuity formula, or especially the growing annuity formula. No one trusts this thing. If you see something like this, that's you definitely want to verify what you did there. Okay. This bullet point I think is important. Don't worry so much about memorizing the formulas. In the past, I've allowed students to use a cheat sheet. I'll do something like that this year. So you don't have to memorize it, but just make sure that you're comfortable applying it. Make sure that you've got some muscle memory when you're working through these problems, that you're not doing it for the first time on an exam or something and have to think through the order of operations. Don't worry about memorizing it. You don't need to waste brain space on that, but make sure that you've done it and you can apply them when needed. Okay, so let's do an example with the kind of ugly growing annuity formula, and then we'll verify it. We'll set things up in Excel and see that we can verify it and kind of check out this formula here. Okay. So let's do it the hard way. Let's do it with a formula first. Okay. We want to find the present value of a stream of cash flows that starts at $100 in 1 year, and it grows 3% per year for 10 years. And we've got a discount rate of 10%. So let's first draw out the cash flows, make sure we're all on the same page here. The cash flows start in 1 year at $100. So go up to this table, We have $100 at time 1. I'm going to make some space here. I'm going to delete some of these cells. At year 2, we know that it's a growing perpetuity, so it's going to grow at 3%. If it started at 100, by year 2, it's going to grow to 103. Likewise, at year 3, it's going to grow again at 3%. So we had 103 at time 2, and it's got to grow at 3% from there. So that's going to take us to about 106.1. So you can see right away it's going to be a pain if you want to value each cash flow. You've got 10 cash flows, and you have to calculate the growth each time. It's going to be a bit ugly to do that. Okay, so let's do it for time 4. What's the cash flow going to be at time 4? Well, it was 106.1 at time 3, and then you got to grow that again at 3%. Okay, and I don't know what that is off the top of my head. Something like 109, say 2, something like that. Okay, then we're going to have 10 cash flows. So let's create some new rows that I just deleted. We're going to skip years 5 and 6, 7, 8. Okay, we're going to get to year, just go straight to year 10. What are we going to get at year 10? Well, we started at 100, and we know we're growing at 3% per year. Okay. How many times did it grow? Well, it's growing at 3% per year from time 1 to time 10. So that means it grew 9 times. It started at 100 time 1, and then it grew 9 times from time 1 to time 10. So we have to multiply, we have to use a 9 in the exponent here. Okay, so let me just free up some space here so we can see what's going on. Okay, so these are the 10 cash flows. It would be a pain to do this on your calculator. We'll do it in Excel. It's actually not too hard to do this in Excel if you just got these 10 cash flows. First, we're going to plug it into the formula, see what we get, see that we have some benchmark that we can check when we go to Excel. Okay, so what's our formula for the growing annuity? Well, I'm going to pull out the R minus G terms. So you can use the formula in the notes, or you can use mine, which is a little bit simpler, I think. This cash flow should be subscripted 1, right? The cash flows here change each period in a growing annuity. It's a big mess. All you need in the formula, though, is the cash flow at time 1. Okay, so that's going to help simplify things when we use the formula. Then we've got this bracketed term. We have 1 plus G in the numerator, 1 plus R in the denominator, and that whole thing is raised to the T, how many payments there are. Okay, so this is the growing annuity formula. These are the first 2 steps of any present value formula, any present value problem. Find the cash flows, make sure you know what the cash flows are so that you have the appropriate formula. And then the next step would be putting the right numbers into the formula. So here, what's the first cash flow that we're getting? That's $100. That's given. What's our discount rate? Well, that's given at 10% per year. What's our growth rate? That's 3% per year. Okay, so the denominator there is going to be 0.1 minus 0.03. And then we got to work inside the brackets. We said that the growth rate is 3%, so that goes in the numerator. Discount rate is 10%, so that goes in the denominator. And that whole thing gets raised to the 10th. It's a little bit ugly, but it's doable. And then you have to make sure that you're comfortable with the order of operations. So again, I'm going to work on this outside term just like I did for the annuities. What's 100 divided by 0.07? That works out to 1430. Then I got to work on this bracketed term. I'm going to calculate the thing inside the brackets, the innermost brackets here first. 1.03 divided by 1.1. That turns out to be 0.936. And that whole thing gets raised to the 10th. Now I'm going to calculate the exponent. So 1430 times 1 minus 0.52. Okay, so we're left with 1430 times 0.48. And that ends up to be about 688.37. Okay. So it's a lot of work, but you can get there. You have to be very careful in working through the formula. But doing this is going to be easier than calculating the present value of each individual cash flow. Because to calculate the present value of each of these cash flows, you have to first find the cash flow that's growing at this G, and that's a little bit hard to do. Whereas if we're using the formula, all you need to know is that first cash flow. You don't have to worry about what the cash flow is at time 2, time 3, whatever. Okay, so let's hold on to this, the 688. I'm going to set things up in Excel, show you how you can check your work in Excel, have Excel do a lot of the computation for us, and hopefully give you some skills for work. My goal here is to give you a few building blocks in Excel, some very powerful building blocks that then you can run with and you can use however you see fit. But I'm just going to give you these tiny pieces and then let you run wild with it. Okay, so this spreadsheet is up on the Teams folder. You can see there's all these different tabs there. I'm going to start from scratch, but everything that I do is already documented and up on Teams. It's just in the class materials folder. It's titled Discounting and CAPM Practice, Excel Practice - Discounting and CAPM. First, let's set up a very simple present value calculation in Excel, very modular setup. So what are the ingredients for any present value calculation? You have to go all the way back to the beginning of the slide deck. We've got these 3 ingredients. Right? We've got the timing of the cash flow, T. We have some discount rate, that opportunity cost of capital, that kind of ethereal thing, the discount rate, R. And then we have the actual cash flow itself, C. Okay, so those are our ingredients. Let's just pick stuff randomly. Let's just calculate the present value for one cash flow with these 3 ingredients, and then we'll see how to expand that and build upon it. Okay. So let's pick a cash flow of $50 with a discount rate of, say, 7%. I'm just randomly picking numbers here. And let's say this thing occurs 334 periods from now. Okay, so just random numbers. The easiest way to start calculating a present value is to calculate the discount factor. Right, the discount factor is just the present value of $1. That's kind of a nice intermediate step before we calculate the present value of $50. Let's just calculate the present value of $1. So I'm going to create a new column for the discount factor. And if you remember the discount factor, it's just the present value of $1. So we're going to type this formula for the discount factor into Excel. Now, how does Excel know that it's a formula? This is the first trick I want to teach you that's very powerful. You can use formulas by typing the equal sign into Excel. So hopefully you can see that. I'm going to zoom in a little bit into my spreadsheet here. Okay, I just typed numbers in TR and C. I'm going to enter an equal sign. Excel now knows that this is a formula. Well, what is the discount factor? What is the formula? It's the present value of $1. Okay, so that's what goes in the numerator, 1. Then we're going to divide it by 1 plus R. Now R, where's R sitting? Well, we typed it in already. We typed it in cell B2. Okay, so this is a very useful trick too. You can refer to cell B2, and then Excel is going to look for R in cell B2. Okay, so that's the first step of the discount factor, 1 divided by 1 plus R. Then we have to raise it to T. So we have to use this little caret thing here. It's on the number 6. You hit Shift 6. It gives you a caret. That's an exponent. What do we have to raise 1 plus r to? We have to raise it to t. Well, where is t sitting? We tell Excel, look in cell A2 to get the time period. And that's the discount factor right there. It's 1 divided by 1 plus r raised to the t. All we did is we told Excel to look for r in cell B2, and we told Excel to look for t in cell A2, and then this whole thing is a formula. So Excel is just going to calculate this whole formula for us. Okay, so I hit enter, and then we get a discount factor. Okay, so this is a case where t is so far out that the discount factor is basically 0. Okay, this is a real funny number. So I'm going to change this to just 15. Okay, just so we can actually see what's going on here. The discount factor here is 36 cents. So $1 that you get at time 15 with a discount rate of 7%, that $1 is only worth 36 cents to you. Remember, that's what the discount factor means. Okay. So if we get $50, what's the present value of this $50? Well, that's going to be 36% of 50. That's how we interpret the discount factor here. Everything gets marked down. It's 2/3 off, or these are the dairy products or whatever we said that expire tomorrow, so they're sold at a huge discount, only 36% of list price. Okay, so that gives us the present value. Present value is the cash flow, which is in cell C2, times the discount factor. Each one of those those dollars that we're getting is only worth 36 cents. So the present value of all those dollars is only $18. Okay. And again, just like I did with the discount factor to calculate the present value, I typed in the equal sign. Now Excel knows that it's a formula and it's going to evaluate it. Where is the cash flow sitting? It's in cell C2, so I pointed Excel there. Where is the discount factor sitting? It's in cell E2, so I pointed Excel there, multiplied the two together. That's how I got the 18.2. Okay. So that's the most simple thing you can do with Excel. It didn't save us any time here because you could have done this in your calculator pretty easily. I just had to type everything out in Excel. So as it is, that didn't help us much. However, Excel is going to be powerful if we have a lot of cash flows. Okay, so let's do that. Instead of having just one cash flow that we calculated the present value for, we're going to just have a whole bunch. Okay, so let's change our parameters here. Instead of having one cash flow, let's say we have 10 cash flows. Okay, so we're going to start at time 0 and go through time 10. All right. So first cash flow is at time 0. Now the next one's at time 1, time 2, time 3, time 4, 5. Okay, one way to do this is to type every single number out, but that's kind of a pain. Yeah, that's not saving us a whole lot of time if we have to type every number 1 through 10 or 1 through 3,000 or whatever. So what trick can we use? We learned how to use formulas already. We saw that with the discount factor and present value. If we give Excel a formula, Excel will calculate it for us. So a useful formula, if we just want to add 1 to everything, I'm going to tell Excel, there's a formula here. Look in the previous cell. So I'm going to look in cell A2, and then I'm just going to add 1 to it. So Excel is going to look in A2, it's going to be 0. It's going to add 1 to it, and that's going to give us 1. And then you can do the same thing for the next cell. Okay, I'm going to look in cell A3 and add 1 to that. That's going to give us 2. Now the problem obviously here is now I'm just typing in 10 formulas. That doesn't help us either. Okay, so here's the second trick. Maybe the first trick I taught was using the formulas. The second trick is filling down formulas. This is really where Excel comes in handy. We can type the formula in one time and let Excel do it a million times after that. These are the basic steps to fill down a formula. I typed in the formula once in cell A3. Cell A3 is just saying, look at A2 and add 1 to it. So we're just counting by 1. So I'm going to select that formula cell, and then I'm going to highlight the cells below it. Okay, that's the second part here. You select the formula, you highlight the cells below it. I'm going to hit Shift and then select, say the next 9 cells. So now I'm highlighting everything here. Selected the formula, I've highlighted the cells below it. Now I'm going to hit Control and D at the same time. I'm going to hold the Control key on my keyboard and then hit the D key, and the formula fills down automatically. I didn't have to type it once. I typed it once and that's it. So I want to get 10 cash flows. So I'm going to fill down so I get 1 through 10. Okay. I'm going to do the same thing with the discount rate. I want to keep the same discount rate as I had before. So I'm going to tell Excel, where do you get the discount rate? Well, just pull it from cell B2. So at time 1, what's my discount rate? Just pull it from B2. So there it is. And then I'm going to fill down that formula too, so that every period, every cash flow has the same discount rate C, or 7%, excuse me. Okay, now cash flows, for now I'm just going to pick random cash flows. I'm just going to kind of mash my button here. I'm going to throw in some negative numbers, positive numbers, let's have some big numbers, see, who knows, maybe it'll be positive, maybe it won't be. Who knows what the net effect will be. Nope, can't have that. All right, so just completely arbitrary cash flows. If you do this on your calculator, you're probably going to make a mistake. There's too many weird numbers here, and you've got to calculate too many things. But Excel, as long as you're comfortable with your formula, and as long as you calculate the formula, you put the formula in correctly one time, then Excel can do this for us, no problem. Okay, so we have the formula for the discount factor already. We know that that's just a present value of $1. Oh, this is a good check. At time 0, what's the discount factor? It should always be 1, right? At time 0, you're not going to discount the cash flow that you're getting at time 0, right? That money is as good as in the bank, so you're not going to discount that at all. It's not on sale. We're going to fill this formula down, and what Excel's going to do is it's going to calculate the formula the same way it did in E2, but now it's going to do it for every cell below that. It's going to pull the time from column A, time period here. It's going to pull the rate from column B, and then it's going to calculate the discount factor. Okay. So I select the formula here that's sitting in E2. I highlight the cells below it by you can just click and hold and drag, or you can click, hold the Shift key, and then click again on the bottom, right? There's different ways that you can highlight these things. And then you hit Control plus D. And here's another useful check. The discount factor should be descending, right? As things go out in time, you're getting more and more of a discount on those future cash flows. They're just worth less to you the further out they are in time. So that's a good check. We start with a discount factor of 1, so no discount. Now at time 1, each cash flow that you get there is only worth 93 cents on the dollar. You go down to time 7, those cash flows are only worth 62 cents on the dollar. Okay. So we can fill down the discount factor real easy. We didn't have to do anything new. We just fill down the formula. Likewise, we can fill down the present value very easily. The present value is just pulling the discount factor from column E, and it's pulling the cash flow from column C. So I select the formula. I highlight all the cells below it that I want to apply the formula to, and then I hit Control D. And that's going to give us a present value of all of the cash flows. I just mashed buttons to get a bunch of cash flows. Excel doesn't care. Excel can calculate the present value of mashed numbers just as easily as well-planned and thought-out numbers. So Excel calculates the present value of each of these cash flows. Okay. The present value of that first $50 is 50. That makes sense. That's good. That next $9,000 payment, what's the present value of that? Excel says that's only worth $8,400. Go down the line. The very last payment at time 10, how much is that worth? Excel says that's worth $24. And that sounds about right? With a discount rate of 7% over 10 years, you get a discount factor of 50. So a payment of 48 should only be worth $24. Okay. Now we're not quite done yet. We want to know what's the value of all of these cash flows. What we've done so far is we calculate the present value of each individual cash flow. So how can we get the sum of everything? Here's another trick. Excel has built-in functions. For example, they have a sum function. The sum function does what you think it is. It just sums up everything that you put inside the parentheses. So let's put up a cell at the very top here. We're going to call this total NPV. Total NPV is just the sum of all the individual present values. So I'm going to add all those up. I'm going to use the sum function here. So I type equals, Excel knows it's a function, sum, add a parentheses here. The sum function is just going to add up everything I put inside those parentheses. So I'm just going to click and drag and put all of these present values into the sum function. And then I'm going to close the parentheses, hit enter, and then Excel tells me that the present value of all of these things is negative 27,000. Okay. So if you're CFO of this company, you see this project with these very odd cash flows, you would do this analysis, NPV analysis, you forecast the cash flows, you get the discount rates, you discount the cash flows, and you add them all up. That's what we saw with NPV analysis. And you apply the NPV rule. Here, NPV is less than 0, so you would say this is a bad project, we're not going to take this project. What's nice about this setup is the formulas are all in place, so I can go back and I can just, change numbers however much I want. What automatically happens is the formulas update. Okay, so as soon as I change that $9,000 to $9, you see that the present value changed from about 8,400 to 8.4. And then likewise, the total NPV also updated because that's just pulling numbers straight from the present value column. Okay. So this is the power of Excel. Once you get the formulas down, you can kind of change your inputs. These are your inputs over here. You change these things however you want, and you'll get a new number and you can check. Okay, so let's say instead of minus $50,000 at time 5, it's just minus 5,000. Now the NPV is getting pretty interesting. Right now we're only at minus 800. Okay, so you can fiddle around with it, make sure that you kind of understand what's going on with Excel here. So let's apply this to that real ugly growing annuity formula that we saw. We calculated this growing annuity and we got the answer here, 688. Okay. Let's double check that in Excel. I'm going to pull up the problem here. I'm going to dock that on the right, and I'm going to set up Excel on the left. So we want to set up this stream of cash flows. It starts at $100 in a year and grows at 3% until time 10. Okay, so first things first, let's get the cash flows down in Excel. Here's our column for the cash flows. What's happening at time 0? Well, nothing. The cash flows don't start until time 1 in this problem. When we drew out the cash flows in the Word document, we saw that. So nothing's happening here. Going to get rid of all those old kind of arbitrary cash flows. The first cash flow is $100 at time 1. Okay. What happens after that? Cash flows are growing 3%. We can use a formula to have Excel calculate those cash flows, in the blink of an eye. I'm going to enter equals. Excel knows it's a formula. I'm going to tell Excel to look at the last cash flow. That's in cell C3. Pull the last cash flow of 100, and then just grow that by 3%. That's what the problem is telling us to do. So how do you grow a cash flow by 3%? You just multiply it by 1.03. And we see that $100 turns into $103 the next year. We have this formula. We're just going to fill it down like I showed you before. Highlight the cells below it, hit Control D, and right away we get all the cash flows for this ugly growing annuity. We didn't have to mash our calculators. It just pops up once we get the formula down. Okay. The next part of this problem is the discount rate. So we just kind of put in 7% here, but we can change one input. We can just change it to be 10% up here. All those discount rates change to 10%, and that's it. That's all we needed to do in order to value this ugly growing annuity. Once we had the basic infrastructure in place, once we had the setup correct in Excel, Excel calculated the present values based on what we gave it over here. We just gave it a different discount rate and different cash flows. Excel can handle that no problem, just calculated a new present value. And spoiler, what happens to the total NPV? It changes to 688. Well, that should be familiar because if we pull up our Word document where we did this before, that's exactly what we got here, 688. Okay, so we use this ugly formula, we got 688. You can check your work in Excel to get the same thing. Okay. So that's why I think Excel is very valuable. You see what's going on. Kind of, it's much easier to feel comfortable with it when you see each piece. You have little pieces and you add them up to get the right answer. That's a little bit easier for me to understand than working through a formula like this over here in the slides. Last thing I want to show you, if you can do present values in Excel, then you can also calculate future values. So we can set up this table here. Instead of calculating the present value of every single cash flow, we can calculate a future value of all of them. So let me show you what I mean here. So let's get rid of the present values. All these tricks are all documented up in Teams, so I'm going to get rid of that. I'm just going to leave the inputs the same. I'm going to leave the discount rate and the cash flows the same. I want to show you how to calculate the future value. When we calculated present value, we first calculated the discount factor. That's the present value of $1 in the present. We want to get an analog to that. So we want to get the value of $1 in the future. Okay. This is how much a dollar in the future is worth at the present. The analog for future values, how much is a dollar in the current period worth in the future? Okay, so let me write out exactly what I mean. Let's say we want to calculate the value of all these cash flows moved to time 10. Okay, so we want to get a future value of everything sitting in time 10. Instead of getting a present value of all the cash flows, we want to move all the cash flows to time 10. Okay, so how would we do that? Well, if we're sitting in year 0, how many times do we have to move the cash flows forward to get to time 10? Well, if we've got $1 at time 0, we have to grow it at 1 plus R. Okay. And how many times does it have to grow to get to time 10? Well, it's got to grow 10 times. So we're going to have to use our future value formula. We got $1 times 1 plus R raised to the 10th. And how am I going to do this? I know I want to move everything to time 10. I know I'm currently sitting at time 0. So how many times do I have to move forward? I have to move forward 10 minus the current period. So $1 at time 0 is going to grow to about $2.6 at time 10. And once you set up this present value with this future value formula, now we're doing future values. Once you set it up once at time 0, again, you just fill down and you get the future value of all those other periods. And again, this is a nice check. We want to know what's going on at time 10. What's the value of $1 at time 10? Well, if you're sitting in time 10, a value of $1 in time 10 should be worth $1 in time 10. Right, so this is the opposite of the discount factor. Right? The discount factor is descending over time. Here, the future value should be descending until you get to that future date. If I want to find the value of stuff in time 10, then the value of $1 before time 10 is going to be decreasing once we get to time 10. Okay, so it helps to work through the formula and kind of think about what's going on and have these little checks as you go. Okay. So now, if we know the value of $1 at time 10, we can calculate the value, the future value at time 10. So I'm just going to call that FV at time 10. Future value of the cash flow is the value of $1 at time 10 times the number of dollars that you have. So at time 0, you don't have zero, you have $0 here. You know that each dollar is going to grow to be 2.6 by time 10. So you multiply those two together, and then you fill down that formula again. And here's, again, a nice check. If you've got $130 at time 10, that's worth $130 at time 10. If you got $100 at time 1, that's going to be worth $235 at time 10. So let's imagine that this is a savings plan. You're saving for retirement, you're saving for your kids' education, something like that. You draw out how much you think you can save each period, but you want to know, how much am I going to have total at time 10? Well, you figure out how much each of these is going to grow to time 10, and then you just add everything up again, just like we did with the present value. You can add up a bunch of future values, and this is going to be your total savings at time 10. You're going to have $1,785 if you're saving this amount each period, and you have a discount rate of 10% on your savings. Okay, so I think that's everything I wanted to do in Excel. You get a few tricks. I documented them in the next tab. You can use formulas. It's got built-in formulas, or you can do it yourself, or you hit equal and you can type in whatever formula you want and refer to the cells where your data is. It's got these built-in formulas like sum, and then you use fill down to make Excel do the formula a bunch of times. It could be 100,000 times if that's what you wanted. Here we just did 10, but the point is Excel can do it in no problem. And so you can get an arbitrarily complex stream of cash flows, arbitrarily long stream of cash flows, and it's not a problem for Excel at all to value that. So this is useful for you to check your work and kind of advance. You can build on this and do a lot with just these few simple ingredients. Okay, so that brings us to the end of this lecture. Just to recap very briefly, we know that the present value formula is very simple, but there's an awful lot going on with it. So we talked about some of the intuition behind it. What do we mean by a discount rate? What's the economics behind that cost of capital? That's the pain that you feel when you're not able to spend your money, basically. If you're forced to keep it in your pocket, that's a cost that you should be paid for. And then likewise, the risk of those future cash flows gets embedded in the time value of money as well. So those are the two things that are driving that's kind of the economics behind everything that we've done today. Beyond that, everything's just moving cash flows backwards and forwards in time. So if you can calculate a present value, you can calculate a future value. It's all the same thing. Talked about additivity. If you can calculate the present value of one formula, of one cash flow, you can do it for an arbitrary number and just add them all up. And that led us to this very important NPV rule. If you're calculating the present value of a bunch of different cash flows, you're putting them all on an apples-to-apples basis. You can compare all of those present values. They're all equal. You can compare each of them to the cash in your pocket. And so if you just sum up the present value of all of them, if that sum is greater than 0, then you know that you're making money and it's a good project. That was the heart of the NPV rule. Then we spent a lot of time on shortcuts for special streams of cash flows. And we said these streams of cash flows are good shorthand for thinking about firm valuation. We're going to see them a lot going forward. And finally, we talked about Excel, and we saw that it can check our work and give us confidence in what we're doing. Once we can kind of see the inner workings of the cash flows, it gives us a stronger sense of the formulas and of what's going on. Okay, so that's all I had for today. Hope everyone stays safe, and I'll see you next week.